recording. So first week, normal force is the subject, and let's see the theory part first. And this is from this It's Learning environment. And this is a brief close-up of these days or this week's subject. So here we start. I have to change a little bit my layout here. And here it says, okay, you can look from the picture also. So the normal force is acting along the length of the beam, and shear force is 90 degrees angle of the normal force. And these pictures you have seen before at autumn when we were learning this statics. This is a beam structure, and this is an individual truss. And when you have joints in both ends supporting this beam, it can only have a normal force in this beam. But if you have a different kind of force in the middle of the joints, then it necessary is not along the beam length. And this one also was discussed at autumn. If we check in this cross section number 1, what kind of force is in the middle, and it's solved here because this left side of the beam and this right side of the beam both have to stay still, and so to do so in both ends have to be same sides of force. And now let's go here. And this is the main subject in this week. So what kind of tension or stress is in the beam? And because this F have to be same size as this force 2 kilonewtons, and force is distributed load times area or cross section. So this is the main equation that we are using today. And also the unit of sigma, which means tension, is megapascal or Newton per square millimeter. Okay, and then let's see what kind of exercises we are having. This is the first one. In this thicker part, there is a tension sigma, and what we have to do first, calculate the force which are causing the tension in the thicker part. And then after we know this force, we can calculate the thinner part tension. And after that, we have to check that the yield strength is not exceeded. So you can't exceed the yield strength at all. And then if it's not exceeded, the stress is in permissible limit. And as earlier, these values you can find from parameter table. Okay, this is the first one. And this picture should also be familiar to you because you have calculated at autumn the force that is in this diagonal rod. But now we calculate also the tension in this cross-section number 1. I have to take this keen bar away. And the last one, there is a brake pedal, and we know this force F with which the pedal is pressed. And there are two things you have to calculate in this cross section, in this connection rod, the tension and also the pressure that comes to the cylinder, brake cylinder. And as earlier, all the values are in the parameter table. So, but now I have sad news for you because my Able pen doesn't work. So I have to walk you through with these tips with the Finnish version because I can't write at the time being. But don't worry, I translate all the titles, so hopefully you can follow the calculation also, even though it's a Finnish version. First I have to change the iPad. Let's see if I can find the right one. I have to put here. Okay, this is the Finnish version, but don't worry, I'll explain all the titles in this site. The first one, what we do is, as always, draw free body diagram, draw FBD. So this number 1 title, draw FBD. Let's see if I can just a little bit. So yeah, I can show this with my finger. So draw a free body diagram, FBD. And what you do, you draw as simple version of this axis as you can. So don't draw three-dimensional drawing, but draw a two-dimensional drawing. After that, when you have drawn this simple version of this object. Then you add all the forces that are affecting to this object. So there is only one force that is affecting this object. Then you take the support reactions away and remove supports and draw support forces. And because there is only axis forces, then we don't have to draw any other y component or moment. This is enough. Okay, now the free body diagram is ready. Then what you have to do next, it was said in the in the exercise, there was said that calculate the force F next. So this one first. And okay, there I have calculated the support reactions, and only this one shows that this AX is as big as this F. And when I have done that, I can draw a load diagram. And these are the sign rules. So AX, when we are approaching from left, is in positive direction. Then the next one is the force F, and it's negative direction. So there is the load in every part of this object is F. And then the next one, solve the force F. And this is the equation that we are using. So we know this one, and we can calculate this one, and then we can solve the F. So this is the equation that we are using. And of course, this thicker part tension we can find from parameter table, but this A1 we have to calculate, and you can see the equation here. Some of you might prefer P R multiplied PD power 2, but I'm used to use this version where is this diameter in the equation. Other way, anyway, you have to calculate this, and this one that you find from this parameter table, and then you can solve the force. Then the thinner part of this axle you can calculate with the same equation. Now you know this F, and you can calculate the cross section of this thinner part, and then you get this tension in the thinner part. And the last was to check that yield strength is not always exceeded. So now you know this one is bigger than this one, and because you know the material of this axis, let's see if I can check which one was it. Wrong Excel. The yield strength is 355, so the S 355 material. So if this tension here, if it's smaller than 355, it's okay. Okay, that was the first one. Let's see the next one. I have to check that I take right exercise. Let's see. Not this one. Let's see this one still. And the material was S355. So yield strength is 355. Not this one, not this one, not this one, this one. Okay, determine the normal tension sigma 1 at the cross section 1,1 of the tension diagonal rod BC. The diameter of the rod is D. See the values in the parameter table. So this tension is supposed to be calculated. And as I said earlier, you have already calculated this one, except the title 3, but these two you have calculated already with this object. So again, draw free body. It isn't easy to show with this finger. Draw free body diagram, and it is here. Free body diagram. The object is drawn as it is. Then the forces that are affecting to the object, there is only this force F. Then you remove supports and replace with support reactions. So in this point A, you have a joint, and when you take it away, you put AX and AY forces or support reactions. Then there is this diagonal rod. You remove it, and because there is a joint at both ends, it can only have normal force. And then you put it here, you see. And at the same time, you divide the force C to the components Cx, Cy. And it's here, so before you can calculate, or of course you can put these equations, but you can't calculate yet because you don't know those components. So what you have to do is solve support reactions, and this title 2 is solve support reactions. And what you can use is the equation of equilibriums or balance equations. You don't. You have to start with this sum of moments to get going. So you write the moment sum to the point R. Cy is trying to rotate counterclockwise, and F is trying to rotate clockwise. And you get this equation, which you can see here. This is very hard to draw with the finger. And when you have written this equation, you can solve Cy. After you have solved this Cy, you have to calculate also this angle alpha. And when you have done that, then you can solve from this equation the force C. And when you have calculated the force C, then you use this equation sigma, or this one, sigma is force per cross section. And that was the final answer. And then there is still this third one. Third one, I have to look that I take it the right version. This looks like good one. So I translate this exercise. The brake pedal is pressed with force F. Determine the tension, normal stress sigma 1, and the pressure P. So this is a cylinder tube for a brake system, and this is the pedal, and this is connection rod connecting this pedal and this piston. Okay, and as earlier, we start always with this free body diagram. And you can see here, I have divided the system to 3 different free body diagrams. First is pedal, then this connection rod, and then this piston. And as you can see, it doesn't have to be curved, this pedal. You can simplify the picture just putting a straight pedal, because those diameters are what matters. It doesn't matter if the F force is a little bit higher or a little bit lower. And then one by one, first free body diagram is this one. There is a joint here, and that's why when we remove the joint, there have to be X component and Y component. And we remove also this connection rod and put the support reaction B. So now this first free body picture is ready, and we can calculate. We want to know this force B. And so we write the moment sum in point A, because we don't need to know these AY, AX components. We only need to know this B. And it looks like that. Px is rotating counterclockwise, F is rotating clockwise. So these moments sum must be 0. And again, we can calculate this support reaction B. And because this connection rod is affecting to the pedal with force P, the pedal must affect to the connection rod at same equal sides of force. It's a law of force and counterforce. And of course, in the other end of this connection rod must be also the same force P, because otherwise the connection rod moves in the direction where the support reaction is bigger. And now when we know this force P, we can calculate the tension in this cross-section asked. And as you can see, there is a compression in this connection rod. So it should be a negative force. And when we have calculated the cross-section area and we know this force B, we put this force B instead of this F, and then we calculate the cross-section and we get this sigma 1 value. And the last thing to calculate is the pressure. And the pressure is in the cylinder tube affecting to piston. And the resultant of this pressure is always pressure times area of this cross-section. So the resultant is pressure times area. And now from this third free body diagram, we know that B must be as big as this resultant. So B must be as big as this pressure times area. And you can see it in here. And when you have calculated this cross-section of this piston, you can solve the pressure. Even though this B value is negative, pressure, when it's greater than normal pressure in Earth, is always think to be positive. So overpressure is always positive value. So you don't put minus sign in here, because this is overpressure and it is positive value. So hopefully you can follow these tips, even though it was in Finnish titles. But otherwise, it's mathematics, so it doesn't matter. In mathematics is same at every language. So any questions? Sorry, I can't help you now because you aren't in here classroom, so I can't more help you. But if you have questions, I can try to explain. So if you don't have any questions, I leave you to follow the instructions and try to solve these exercises. Hopefully next week I have my pen so I can more precisely show every detail.